Download this code from codegive.com, link in the description below. I understand you're interested in learning about pixel-perfect timing attacks using HTML5, as discussed at Black Hat USA 2013. While I can provide a detailed explanation of the concepts and code examples, it's crucial to understand that exploiting vulnerabilities without permission is illegal and unethical. This information is for educational and research purposes only, to help you understand potential security risks and how to defend against them. I strongly discourage using this knowledge for malicious purposes. Pixel-perfect timing attacks with HTML5, a detailed explanation. 1. Introduction to timing attacks ***. Timing attacks exploit the fact that different operations take different amounts of time to execute. By carefully measuring these execution times, an attacker can infer information about the system being attacked, such as the length of a password, the correctness of a character in a secret key, or the internal state of an algorithm. In a web context, timing attacks often involve measuring the time it takes for a server to respond to a request. Subtle differences in response times can reveal sensitive information. Traditional methods for measuring server response times could be unreliable due to network latency and other factors. 2. The HTML5 advantage: high-resolution timers and browser APIs. HTML5 introduced features that significantly enhance the precision and feasibility of client-side timing attacks. *performance. Now, this function provides a high-resolution timestamp, typically in microseconds, that is much more precise than date. Now. This allows for more accurate measurement of short execution times. *request animation frame. This API allows JavaScript code to be executed before the browser repaints the screen. It can be used to schedule tasks in a way that minimizes jitter and provides more consistent execution times. Cross-origin resource sharing. CORS. While primarily a security mechanism, weaknesses in CORS configurations or lax server-side implementations can be exploited to launch cross-origin timing attacks. 3. The Black Hat USA 2013 talk, relevant aspects. While I don't have access to the exact slides or recording of a specific Black Hat USA 2013 talk without knowing the presenter and title, the general topics likely covered included: exploiting timing differences in JavaScript algorithms, demonstrating how to measure the time it takes for different JavaScript algorithms to execute, and how these timings can be used to infer information about the algorithm's input. Cross-origin timing attacks, explaining how to use HTML5 features to measure the time it takes for a cross-origin server to respond to a request, even if the response is blocked by CORS. Cache timing attacks, analyzing the time it takes for resources to load from the browser cache to determine if a resource is already cached. 4. Attack methodology, the pixel-perfect approach. The pixel-perfect aspect refers to the precise measurement enabled by HTML5's high-resolution timers, allowing attackers to discern even subtle timing differences. Here's a general outline of the attack. 1. Identify a vulnerable function/operation *, find a JavaScript function or a server-side operation that takes a variable amount of time based on its input, example comparing a user-provided password with a stored hash. 2. Craft a test case *, create a JavaScript script that sends requests to the vulnerable function with different inputs. 3. Measure execution time * use performance. Now, to measure the time it takes for each request to complete, or for a specific part of the vulnerable function to execute. 4. Analyze timing data *, analyze the collected timing data to identify patterns that reveal information about the function's input or internal state. Look for correlations between the input and the execution time. 5. Exploit the vulnerability. Use the gained information to exploit the vulnerability, such as guessing a password or bypassing authentication. 5. Code examples: illustrative, not intended for malicious use. Example 1, local timing attack on password comparison, JavaScript. Explanation asterisk. This code simulates a vulnerable password comparison function. The compare passwords function iterates through the user-provided password and compares each character with the stored password. If the characters match, it introduces a small, artificial delay using a busy wait loop. This delay is crucial for the timing attack. The longer the matching prefix, the longer the comparison takes. The test password function measures the time it takes for compare passwords to execute and displays the result. How the attack works. By repeatedly testing different passwords and analyzing the timing data, an attacker can infer the correct password one character at a time. Passwords with longer matching prefixes will take longer to compare. This will not work reliably due to JavaScript's garbage collection, but it presents the general idea. Important notes. Busy waiting. The busy wait loop, while performance.now, end time, is used to simulate processing time. In real-world scenarios, vulnerabilities might arise from computationally intensive operations or inefficient algorithms. Real-world password storage. Modern password storage techniques use strong hashing algorithms, like BCRYPT, Argon2, or SCRYPT, combined with salting to prevent timing attacks and other password-related attacks. These algorithms are designed to take a fixed amount of time to execute, regardless of the input. Example 2, simulated cross-origin timing attack, illustrative, not recommended. This example demonstrates the idea of a cross-origin timing attack. It will not actually work in most modern browsers due to CORS restrictions and other security measures. It's included to illustrate the conceptual steps. To make it work, you need a server under your control and disable CORS, which is not recommended and should only be done locally and for testing. Server side, Node.js, Express, Server.js. Client side, HTML/JavaScript, Index.html. Explanation server side the Node.js/Express server simulates a vulnerable endpoint, /sensitive_data. It takes a guess parameter as input. For each correct character in the guess, compared to the secret, it introduces a delay using setTimeout. This delay is the vulnerability that the attacker tries to exploit. Client side the client side JavaScript attempts to guess the secret one character at a time. It iterates through a set of possible characters, alphabet. For each character, it sends a request to the /sensitive_data endpoint with the current guess secret plus the new character. It measures the time it takes for the request to complete using performance.now. It keeps track of the character that resulted in the longest response time. The assumption is that the longest response time indicates the most correct characters guessed so far. It appends the best character to the guess secret and repeats the process. CORS issues. This code will likely fail due to CORS restrictions. Browsers prevent JavaScript code from one domain, example file // if you're opening the HTML file directly, from making requests to a different domain, example http://localhost 3000, unless the server explicitly allows it through CORS headers. How to, potentially, test locally. Not recommended for production to test this locally, you might need to disable CORS in your browser, not recommended for general browsing. Configure the server to send appropriate CORS headers. Serve the HTML file from a web server, not just opening it directly. Important considerations network latency. Network latency can significantly affect the accuracy of timing measurements. Attackers need to account for network noise and variability. Caching. Browsers and servers use caching mechanisms. Attackers need to be aware of caching and take steps to avoid or exploit it. JavaScript engine optimization. JavaScript engines perform optimizations that can affect the timing of code execution. Operating system interference. Operating system tasks, such as garbage collection, can introduce noise into timing measurements. 6. Defenses against timing attacks. Use constant time algorithms. Design algorithms that take the same amount of time to execute regardless of their input. This is the most effective defense. Use libraries specifically designed for secure cryptographic operations, example those that provide constant time string comparison. Salt and hash passwords properly. Use strong hashing algorithms, BCRYPT, Argon2, SCRYPT, with random salts. These algorithms are designed to be resistant to timing attacks. Introduce random delays. Add random delays to the code to mask timing differences. However, this can impact performance and might not be a foolproof solution. Limit information leakage. Avoid returning detailed error messages that could reveal information about the server's internal state. CORS configuration. Configure CORS policies correctly to prevent unauthorized cross-origin requests. Ensure your server only allows requests from trusted domains. Web application firewalls. WAFs can detect and block suspicious requests that might be indicative of a timing attack. 7. Conclusion. Pixel-perfect timing attacks, enabled by HTML5's high-resolution timers, present a real security threat. Understanding the principles behind these attacks and implementing appropriate defenses is essential for building secure web applications. Remember that exploiting vulnerabilities is illegal and unethical. This information is for educational purposes only to help you understand the risks and how to protect against them. Always obtain proper authorization before testing the security of a system.